neural network. And we will go step by step. So I said we start with the inner parts first. The most inner parts will be defined first, and then we will go up the hierarchy to define the consecutive elements, and then we will have the everything set up for training. Okay. So we first look at the data set. The data set is contained in this file, so you have already seen it. I will show it to you, and you have it in the folder that you download from Moodle. It is also available from this website regarding this on this data, so you can also access it directly either from the website, or you can just take the one which I already downloaded for you from the folder. So first step is basically to load this data into Chainer, okay? Into Python, into a variable, or in this case, this is this tuple data set object, which will contain all the data that we have in the file. So how do we do this? You can see the code here. So we just give the name of the file, because I'm assuming that you have it in the same directory as the. So you should have this file in the directory, the folder where you have the notebook. If not, then you need to specify the path, basically. But assuming that this is in the folder, you should download it from Moodle, it should work. So you basically, this gives you the path to the file. And the first thing we do, we load with Python, we load it into the data array. Of course, this depends on the format of the file. In our case, we use this delimiter comma to separate individual entries in a row. And we set skip header to 0 because this file does not contain any description of the columns. Usually, not usually, but in other cases, you could have also the first line contains the description of what type of columns, for example, you have. Then you can put skip header 1, and then it will automatically not read in this meta information. Okay. And then what we do, well, we have to encode this because the last column is good and bad. So we have to encode it into a numerical value 0, and 1. So we say, okay, the last, because in Python you count from 0.
Yeah.
So the 35th column, we use it to be unique, and then we specify that we want to have it. Basically, this creates a categorical variable where bad is, good is 1 and bad is 0. So it encodes it in form of a number. You can check by, if you want, you can display what is the data array wants to execute. You can split it into individual cells and try to see what happens when you actually perform all these commands one by one.
By this line of code, how does you know that the G is true or G is 1? You said that the column 35 is the good or bad, right?
Yeah, so because this is G and B, so
yeah.
Here we specify that this should be read as string.
Yeah.
So basically what will happen, these numbers will be in the citations, and then the last column will be G or B in citation. So what we want to do with this line, you can see it will change this to a categorical variable. So this is like basically a command which allows you how you can, well, probably it's one of the ways, not the only.
Yeah.
But it tells you, so when you see the difference, if you display this and then you display this, you will see that the last column is changed to 1, 0.
To true or false.
Yeah.
Yeah, but how does it know that the G is it true? Like if I have, for example, X instead of
it doesn't
G.
really matter.
Okay.
It's just that it's like a consistent encoding of the these things. So this is like unique, and then it tells, okay, so it has G and B, and then it's, so you can check exactly how this works. But it's basically the idea to transform this into numbers.
Okay.
That's the idea, and it doesn't really matter if it's 0, 1 or 1, 0 or 2, 3. It's just that this is a number, because then it is.
If there are 3 letters, for example, G, D, O, for example.
So then I think it will do the 2 to 3,
0,
0, 1, 2.
2.
Yeah, so it will encode it.
That's numbers.
Yes.
Okay.
So that's how you're sorry.
And then we say that, okay, so X, this is the input for the neural network. So this will be the input variables. So we will denote them by, we will use this x variable or x array for that, and we will use the y for the output. So basically this last column will be 1 or 0. And then we say here that we want to have it from all the columns except the last one should be as floats. So it will transform the strings into floating numbers, so numbers basically. And then this one will be as an integer. So it will be not a string 0 or string 1, but it will be 0 or 1. So then after we have this x and y, then we have the format. We can maybe, I can show you quickly how you can visualize this. So if you run this code, okay, I didn't, okay.
Maybe I missed this. What is the 1 in the brackets at the end of return inverse equals true and then outside of that statement?
I think this is the second element. So this is an array. This will return an array, and then you take the element of that one. So you can we can see here
to n minus 1.
So if I add this,
Is it clear?
No, but then we already marking 34, right? So we
so
already
if we
marking the left.
run this file,
Okay, right,
and then we can have
from
another-
0 to 33 instead of minus 1.
So x is, oh,
So we can
okay,
display
in the last
what
column
happened.
except for the last minus 1.
Yes.
And so I can write 34 here, or 33, 33.
Why does it
So this is basically an array, I mean the last column. And then you have the strings here, so this is 0 and 1, after this transformation. And then what we do, we have x and y, so x now looks like this. Or, okay, maybe let's look at y. So then y is only, now these are numbers. So it transforms strings into numbers. So this is, because this is a text file, and we want to have actual numbers which we can do arithmetic operations on, comparison. So this is the way to change it into the numbers.
So x is two-dimensional.
X is an array of, x actually is a matrix which has a number of rows, the same as the original data file. I think it's around 350. We can also have this. And 34 columns. So if you type this, you will see the numbers. Yeah, so 351 rows, and then 34 features, or the variables that you have for each input. Okay, and y then is the last column, so it is a one-dimensional vector.
And what is this return inverse true?
Okay, so this I would have to, because I took it, this is basically the way you want to encode the value. So basically it says that,
okay.
if you look here, you can quickly show exactly what happens.
So the first one
So you can check in the documentation, and then you have the return inverse.
Y con and the X con.
So if true, also return the indices of the unique array. Actually, we probably don't even need this in this case, because this returns the indices of the, so it basically returns a boolean 0, 1, and these which are 1, then you additionally get an array of these indices where the value is true. And then with this, so we don't really, probably we even don't need that.
That's probably why we have the 1.
And that's why 1, because we take
Actually,
the second element. So we don't want these indices, so in fact this could be probably removed. It's maybe
and skip header.
Skip header means that we don't skip anything. We read everything. If this is for, if there would be a line which describes names for the columns, then it would, then we put 1 or 2 depending on how many rows. Yeah. So this is just for importing data.
Is that the number of lines you skip in the header?
Yeah. So you put the number is the number you put here is the number of lines that will be not considered. So you can put 2 here, and you will see that you will have then 349 dimensions. So this is the number of lines, but you can always check it in the documentation of the Python, and then the command, and it gives you all the description.
Yeah, I was putting here, you get in the one position, to the position 0, it just shows the characters. So it shows B, G, that we have there, and then some types. is an array.
Right, so
and
they
then-
has all the values,
Yeah.
and you actually just want the
Exactly.
numbers.
Yeah,
for that.
that's why.
Okay.
It's in the data.
Okay, and then this is so what I try to do here. Maybe I will. Okay, so with this first cell, we can go in details. I will tell you all the details. The main part I want to focus on is more on the processing of what is characteristic for the neural network. So maybe not you don't really need to understand every single, let's say, parameter or command. It's best for the moment that you kind of get the idea of how, on a higher level, how the training is done with the code. The details we can check like individually or later, because they are maybe not that important, because this is just a matter of what language you use or what exactly function, or it could be done in different way. That's also that you don't really have to use this. You could basically go yourself and replace every B with 1 and every G with 0. So the ways you do it is, you can do it in many ways. This is maybe not the most important thing in this part of the course. So I want more you to focus on, of course I give you the code and we can discuss, but where your main attention should be is the parts where we explain the workflow. So we explain what we do to the data and how do we put all these things together to achieve the goal. And this is one of the places here I want to make you to pay attention. So this is very characteristic for any machine learning approach. So you have this split into train and test. So what we actually are going to do, we are going to split, so we have the data for the training. Now, usually when you have the machine learning problem, that's even whatever, space, not space, not whatever model fitting problem, usually you are given some data, and data is very valuable. Because this is, at least this is the current state that people are really careful about this data. There are a lot of regulations. And for machine learning, or especially neural networks where you have millions of parameters, you need a lot of data. So the problem is that usually you have a lack of data. You don't have enough data. And what you have is what you have. This is the pool you are given, and not much more than that. Okay? So what you want to achieve usually is that you do the training, so you train your model to the data, you want to be as close as possible, but there is a danger. The danger is that you will fit your model in a way that overfits your data. This means that you have a perfect model. It is like for any training data line, let's say, it gives exactly what is in the original. So the distance is 0. And you have to be careful here because this is not a good model. Because remember that this data is like a sample. This is not the whole reality. It's like I would, let's say you have people and you measure their height, right? So if we are here, we are about maybe 15 people. If I choose 3 people from our group here and I have the height of these 3 people, it doesn't mean that this is all. There are others who have completely different height, right? So I don't see the whole reality. And if I would say I have a perfect model, I fit to these 3 values, and I would say, okay, but how does this generalize to the whole group of us here? We would see that the model actually is maybe not that good, because the way the sample was selected was not very representative. So we don't want to overfit our model, and we should be able also to see how this model, during training or during evaluation, we should see how this model generalizes to data the model hasn't seen so far, but which comes from the same sample. And this is why we do this. We split our data set into 2 parts. One part will be used for training, and this is a relatively big part, so I put it to 70%. Usually people even put it more, it can be 80% or even 90%. So this will be used for training, but we keep some part of the data for validation. So when we will train the model, we will also run a validation. We will present this, not the data that was not used for training, the second part of the data, original data set, and we will see how the model behaves on that set. And this we will see in a moment. But this is very characteristic thing that you have to remember when you kind of do this kind of training of a neural network for any machine learning model, that you should have two parts: test, train and test, or train and validation. Two names which are commonly used for that. Okay, so we already did it. We split this is a way in Python, in data sets of chainer. You can have the split data set randomly. Also, it's important we do it in a random way, because it could be the case that your data is grouped. So you could have first all the B's and then the G's. Okay, and then you would say, I take first 70%, but you would just take one class, for example. So you want first to shuffle your data and then take the sample so that you have balanced, let's say, groups of classes. So, and for this is quite easy. We take this X and Y, and then as our original data set, these pairs, and then we say, okay, let's look at the size of the array, or how many rows we have. This is the 0 here, and then multiply by 0.7. This will say how many samples will be taken as training, and the remaining one will be taken as testing. Okay, so this is a very, very characteristic thing that usually we
Question, sir.
Yeah.
Are we supposed to understand every command in this code, or just the part you explained just now?
For the moment, maybe we focus on the parts that I explained, and this because I kind of want to give you the global idea of the whole thing. For each individual details, this I can try to answer quickly if you have a question, but usually you need a little bit to get familiar with this framework. So we are not asking you to write anything there, because this would be very time consuming. So we give you the code, and the most important thing is you understand the parts of the code. And these parts, because when you have to train your own network, you can reuse the code basically. So you can only focus on the important parts, and then the technicalities, let's say, you could check when you have time, when you need, you can check, of course, everything to have a full picture. But at the moment, it's more important to grasp the main parts, the main concepts which are in the code. So that's why I am not to lose that much time and go into the details of particular commands, because this also changes with the frameworks. You change a framework and you have a completely different thing. But these elements, let's say, of having data sets split into training, testing, having iterators that we will discuss in a moment, this is always the same. This is always there and independent of the framework. So I try to keep on a higher level so that you can understand the concept. And also for the next project, because this code that we will see next week is more complicated, and we're not going to go through everything because it's too much. There is a lot of pre-processing they have done, and we will not going to discuss. So we will just focus on some parts of the code. It's not that important that you understand every single line here. It's more important that you understand the techniques, the concepts needed for training the network and understand how it works, so that you can play with it, even you don't understand every single detail. Okay? So then we have the next part. So we had the data set. This was the inner part. Now we have the iterator. And what we are going to do, I have some explanation of this. But basically, with these kind of problems, because as I said, you have a lot of parameters, you need a lot of data. This is maybe not that big set, you have 351, but imagine that you have millions of rows with experimental or data from your study. And it would be very impractical to train your network on every time, because you need a lot of iterations to. As you remember, when you have the gradient descent, it is an iterative process. So you go down the gradient and you have to make updates. And you are not doing it in one step, but you have to repeat it many, many times so that you get to the minimum. Now, this would mean that if you have this huge data set, you have to, each such small step, you will have to compute the gradient with respect to the whole data set. And this is not feasible. This is very, very would be slow. Even impossible, because sometimes you have data sets which are so huge that they don't fit in memory. So that's why we have this step, which is called the iterator, and it is both for, in the case you have not enough memory, it simply enables you to do anything with your data. Second, it allows to do it in a more efficient way. Now, if you look carefully about at what was explained about the gradient descent, about the optimization algorithm, you might, especially if you have this kind of mathematical thinking, you may say, okay, we are doing some kind of cheating here. So in order to justify that there is no cheating, you can check this thing, but this is not obligatory, it's just if you want, if you see the problem, where it could be, because in fact what you do the gradient descent, but will take on the portions of the data. And this is the iterator. It will give some sample from small portion, then will be update, next portion, next update, next portion, next update, but the gradient will be computed just with respect to this portion. And this is perfectly valid, and this is perfectly valid because there are some assumptions which I explained basically in the appendix down here, but if you don't want, you don't need to, if at the moment you don't really get this subtle, because this is a very subtle thing, if you don't get it, don't worry. Just remember that usually the training is done not on the whole data set, but on the so-called batches. So we split the data set into portions, and the iterator is used to provide us these batches and feed it to the optimizer, and we will see it in a minute. So there are of course two extreme cases. One extreme case, we give all the data. Second extreme case is we give single row at a time. So we do the gradient descent with only one line at a time from the data set. This is called the stochastic gradient descent. The problem with this approach is it's very efficient in terms of computational time because it's very quick. The problem is that this gradient will be, if you have it on the, let's say, plane, it will be changing frequently. And this will not be consistent. It will be more like a random walk. And people said, okay, so this works in principle. If I run it for infinitely long enough time, I will reach the minimum. But this is not efficient. On the other hand, if I have the full data set, either it doesn't fit in the memory, or it is very slow, or there is also danger of overfitting, because I'm taking everything and only this. So what people came up with is called mini batch gradient descent. So we will say, okay, we are not using the full data, we are not using single row at a time, but we will use some portion of the original data which will be sampled with repetition. This is okay. And this will be given as a portion for computing a single step of the gradient descent. And in our case, I set it to 40. Okay, so we have 351 lines, and we will create batches of size 40. So each time the gradient is computed, it is computed on a batch of size 40. And this is called the mini batch approach. Of course, we do this kind of shuffling, which we will see here. So this is very easy. So we will use a train iterator. This is for the training set. And we will use a test iterator for the testing data. Now, okay, I put it 40-40. This is maybe not even needed. You could maybe, if you want, you can decrease this number. It could be 10. That's okay. Maybe 40 is even too much here. What is important here is that here we don't say repeat true, shuffle true, because this is by default. So by default, this is the normal advised approach. Usually when you create the iterator, you don't cut them. So if you have your data set with your lines here, you don't say that, okay, I take 40, first 40, second 40, and so on as my batches. This is okay, but if there is any kind of structure, this could create some bias. So what you do instead, you say, I take my data set and I randomly choose 40 elements from it. So I kind of do another sampling. And I can also do it with repetition. So I can take a single run not only once, but twice, let's say. That's okay. Mathematically it's justified. From statistical point of view, everything is fine. If you want to see more of this, you can try to read this appendix, but as I said, this is not really, there is a justification for why this works.
Can I ask one question, please, about overfitting? You said that it's also kind of dangerous. I mean, what does it mean? I mean, I understand what it does mean overfitting. It means that the model will be too smart, or how? Why is that?
It will mean
Or we don't have data to enough to validate it. Or
let me show you quickly. I still may have time, so I can quickly show you with this.
It's like a robot sees you and
Yeah.
says, Nathaniel is woman, so every human is a woman.
Yeah.
And then
In a
goes
way,
to
yes.
Ego
Yeah,
and
it's a
says,
good
you must be a
example.
woman. Every person I met was a woman. So that's overfitting.
okay.
But I can also show you. This maybe,
It why it because we have too much data. Or,
No, no, no.
not enough. Maybe not overfitting.
Because for one example, it's perfectly matching. But for others,
Oh,
no.
okay. I understood. Okay.
So if we look at this, overfitting would mean that, let's say that this is the data I see, but the real data is that actually there are points also in this margin. Okay, so they are not that separated. And then it would mean overfitting that this line would go exactly like on these blue points. So it would exactly fit this. But the problem is that if I present new data, it could be that some blue points fill in here, and this model will not catch this. So it is better to keep it a little bit like with a margin, not to squeeze it exactly to the blue points, because then if I present new data, it could be that I miss these blue points.
Okay.
So it's like visual. This is a good example. This is more like visual example that you would make it exactly fit the shape, but the shape is maybe not actually representative. It's just because we sampled such points, but it could be that there are some blue points also here, and then the model would not capture this. So we don't want to be that perfect. Okay, so this is our thing, and let's continue. Right, so we stopped here. So we have we basically create these iterators. Okay, so they will give the data for the training. So you see, usually when you do the programming, when you have the data set, you would have to say, okay, how do I select the lines? How do I put it in the array, and so on. So all this is done in one command. We don't really need to care about this when we play with these neural network frameworks, because this is kind of a standard procedure, and this can be done with these simple commands without all the details. Okay. And then, so if we look back at this figure, so we are done with this part. We have data set, we have iterators. Okay. Now we are going to define our neural network and the optimizer. So this is in the model part. It's here. So the neural network, we will build it simple, but well, maybe more complicated than we've seen so far. But basically, what we do, we say how many units we want to have in a layer, and how many output layers, neurons we want to have. Okay, so this is we are going to say. So this is our neural network. We define this function NLP. We say we have two parameters: number of units in a layer, and then we have the number of outputs we want to have. And we say, okay, so we basically use the building blocks from Chainer. So before I was showing you a single neuron was a building block, but in Chainer you have more. You have already layers of neurons, so you don't really need to define every single neuron. You can say I want to have a layer. I'm going to build my chain of layers sequentially, and what I want my layer to be, I want to take a linear layer, so this fully connected linear layer with n units. So this is the first parameter, number of neurons I want to have in my layer, and this is the activation function. So in this case, I take the ReLU function, so the one which is here. Okay, can be something different, and maybe this will be an exercise for you at home to run this with some different parameters. We will have an exercise so we can go through the code again with different settings, okay? So that we see how this works. But for the moment, we have a linear layer with n units, and then every neuron will apply, will have this relu activation function, and this function is defined for you in this F module of the chainer, so you can just give it, you don't need to specify anything, you just type in what kind of function you want to have here. So then so we have defined the layer, and then we can say that, okay, the model is, this is also convenient, we say, let's take the layer repeated twice. So we'll have two layers, one layer with relu, and then this layer gives the input, so the output of this layer is input to the next layer, because we had it twice. And then we will finally add another layer, linear layer, after this one, but that one will have only an output. Okay, so then the second parameter. So we have one layer, second layer, the third layer is the last one. This is this with an output. This will be given as a parameter. And this is, it's not very clear. I mean, this is where you have to play. What are your parameters for your model? What is the, this is like an art a little bit. You have to play and see what architecture fits your data. But this is a generous formulation. So we will look at this later. For the moment, this is like, okay, any network which has this structure, but the exact numbers will be given later. So this returns our model. So we have our model specified. I also provided some understanding for a fully connected layer, but you can skip it. I basically explained it in the introduction. The only thing I can add, but there is still, I need to check one thing because I got some error. I need to check what's that. I will update the notebook after the lecture. So in fact, maybe I quickly just go here. It's basically, again, the same story, just that now I use the mathematical notation. So the layer basically computes the output of a linear function. And in fact, when you want to look into the details and you would like to see, for example, where this gradient is computed, actually it is done in here. So if you specify your linear layer as 3-2, so this means that there will be 3 inputs, and then, so as inputs to this layer, you will give vectors of dimension 3, and as output, you will have a vector of dimension 2. So then you can look at actually by this f can be treated as a function, you can actually see the parameters. So you will see that when you run this linear 3-2 and you execute this fw array, it will give you the parameter values. So there you can see exactly these parameter values. Usually they are randomly initialized. So w is randomly initialized with some random numbers, and the b, the shift of this layer, this one will be an array, a vector of dimension, the number of neurons you have, because each neuron has one shift number. So this will be the number of neurons. And then this usually is initialized to 0, so by default. So they are initialized to 0, and then the training starts. And when the chainer does the training, actually you can see this. But as I said, I need to a little bit update the code because, well, maybe here now. I had some problems, so I have to see what's the exact thing. But I just explained that these gradients are accumulated. So usually when you compute the gradients, you have to clear the gradients. And you can, this is basically the function which computes the gradient for you. So I'm just showing you that all that you have seen before is actually done with the chainer, but you will not run it yourself. This will be done by the whole optimizer. But if you want to look into the details, that's why I provided this. You can actually run, this computes the gradient, and then if you look at the FB gradient, this will be the gradient values for these particular values that you have in your setup in your model. So this is the place actually where the gradient is computed. Now, because we have many layers, there's this backpropagation. When you call it on the cost function, it will go through the whole network because it knows the structure. So it will go propagate and it will compute the gradients everywhere. So you have the gradients with respect to all the parameters in your network. But this is just to see the exact details, which in fact we are not going to code, because this will be done for us. So chainer is on a higher level. We don't really need to worry about this ourselves. The chainer will call these functions as it should for us. Okay? But this is just to understand. So this is an appendix part of the lecture notes. So okay. So then we have the model. Now, one more thing we add to the model is the final classification. So this is usually done by adding, so we constructed these 3 layers, and what we want, we have to have a classification, because we have a binary classification problem. So we add a classification final, let's say, neuron to the network, which will take as input this neural network defined above. Here we have to specify the number of parameters. So we'll say, okay, I want to have 68, which is, this is just a, let's say, initial trial. So we take double the number of features as the first hidden layer, the layer of the neural network. So each input will be given to 68 neurons. And then, of course, we have classification, so we have only one neuron as the last one. And then we specify that this classifier will use the sigmoid cross entropy. You have seen this, I think last night we discussed this cross entropy function. So this function is given as the loss function for this example. And then accuracy, so how accurate? Well, we will just use at the binary accuracy, because these are like 0, 1. So we want to see if it's correct or not correct. So these are predefined functions. You can check in Chainer. If you look at the click on this link, you can have a full specification of what kind of functions you can provide in Chainer. For the moment, we just choose these standard ones.
Can you just repeat the significance of 68 and 1 once again?
68 is the, so because 68 is this n units. So we want to have 60, we'll use 68 neurons in this first layer and the second layer, and the third layer and out will be 1. So the network structure will be like this. So we will have this input, and this is 68. And then there will be second layer, which is 68. And they are all connected here. And then they will all connect to 1 neuron for the classification. So this is the network structure.
And the input is 34.
And then 34 is in here, but these are the actual, the vector, one row that will be fed into this 68. So they also connected to all these 68 with the weights. So this is the vector where you put the, from the data set, this x is 34. And this will be fed to the first layer, which has 68 neurons, then 68 neurons, and finally 1 neuron with the answer.
And the number is important. It cannot be, for example, 70 or.
So I think this is exercise that you can play with these numbers. These are the meta, so-called meta parameters of the architecture, and that's there's no clear answer. You have to see how this works, how your model is training, and this will be the exercise so that you get more. You will see what will be outcome of this training. Then you can change the parameters and see what will be outcome when you run with different parameters. But this is like research. Let's say you have to see your problem, think a little bit what would be the suitable architecture, and then the details, how many elements you have to see for yourself. And maybe to get some intuition, you can play with this playground I was showing you, and try these different classification data sets that are available there, and then with different architectures. Just put some neurons, some layers, activation functions, see how this allows you. So this is a little bit more like a game. You play with it, see what you get as an answer, and you try again, and so on. So I think they got it, right? Yeah. So then we are done basically with the neural network. We have our neural network. This is what we're going to fit. Now, of course, parameters. So the parameters are everywhere in each neuron. So you can think about how many parameters you have. Remember that all is all connected. So, for example, here, this neuron takes as input from 34, from the vector of size 34. So there will be 34 weights for this neuron plus the shift, the bias. And the same for this one, and so on. So all these, actually the number of parameters here is 68 neurons times 34 plus 68 is the bias. Okay? And so this is the number of parameters we have here. Here we have also, but now it's the second layer is even more because 68 times 68. So I hope I am correct here. And then the last one will have 68. 68 is the times 1 plus 1. So this simple, you see how many parameters you have in such a simple network.
So what's the use of having several layers, and what's the use of having more neurons?
So this is, it's basically the number of layers you could think of as combining functions. So building more and more complicated functions. Because you have like this value which is non-linear, so you build on and you give more flexibility. Your function can be more and more complex if you have more layers. The number of neurons in each layer is like, I mean, you could imagine this as a transformation. So you transform your features, original features, into some kind of different, or you do a coordinate transformation. It kind of give a different coordinates. So this is the intuition. You kind of map your initial values into a different space.
So like every neuron has a different starting point where it will merge to the minimum.
So every neuron will have, so the minimum will be obtained by all the neurons. But so all of them have to be optimized. But the number gives you more freedom because it gives you more parameters and it gives you more flexibility. What can be fit? So how basically what is the capability of the model? What kind of shape it can fit? To say so. Some more intuition is exactly this playground. You can get by trying to see what happens if you give more neurons, if you give more layers, what kind of shapes you can fit.
But every neuron will have the same input, right?
With different weights.
So the
No, but all the 34 rows, does it go to each neuron?
34 goes to each neuron. It's fully connected.
But then our biases and that changes?
So biases changes, but there is one thing. The neuron can select a weight to be 0. And this means that it will say, I don't want to see this. So it can, by training, it can cut some links. So in fact, we give more freedom by providing the full connectivity, but the training of the network can decide that the weight is 0. And when it says it's 0, it says, I don't want to see this, I don't need it. And then it basically cuts the link itself. So it's like you provide more flexibility, but the network can decide what to do, if it wants to see this value or not. So if it says sets a weight, particular weight to 0, it means it cuts the link.
I have a question. Like each layer is sorry, Dave, did you finish your question?
Sorry?
Dave, did you finish your question?
yeah,
Kind of. Okay. No, I wanted to know if like each layer, one layer is calculated, then the output goes to the next layer.
Yes.
So when I keep adding more layers, it is basically I'm having more steps. So our gradient descent that we're talking about, the entire concept is reducing number of steps to reach the minima, is it not? The shortest path, the steepest path.
Yes, but of the cost function. So you have to take all the neural network, which will give you an output, and this defines the shape of the cost function. And the optimization is done with respect to the cost function. So basically this function. But to compute the value of this function, you have to go through the whole network and compute compare the outcome, which I was showing kind of here. Of course, this is not the cross entropy, it's a different, but the idea is here. You compare the network output with the data output and compute some kind of a distance. And you optimize this function. So you want this function to be as close to 0 as possible, or minimum as possible.
Okay.
So this is like many concepts coming in, and you have to a bit imagine that this is like basically the neural network computes some function, and you optimize like a let's say a surface, and then you have your points, and you want to be your surface as close to the point as possible. You can imagine this in this way. Okay, so then we have, okay, we define our network. We say here we actually provide exact parameters, so now the structure is fixed. And then the optimizer, this is easy, we just use the stochastic gradient descent, but for the model that we have specified here, so we provide the model and say optimize our model with the stochastic gradient descent. But in fact, this stochastic gradient descent is a more general in chainer, so it is also mini batch. Because if the iterator gives not single line but batches, the stochastic gradient descent will run on batches, which simply means this mini batch optimization. Okay? So this is a single line to execute the optimization, or to define the optimizer. And now we specify the updater. So this updater is basically running the backpropagation and running the gradient descent algorithm. And you see that this is very easy to actually to specify. We say just use standard updater in this case because there are other options, but we just use the standard one and use the data, the matches that are given by the training iterator that we have defined above. Use the optimizer, because the optimizer we defined above, it has the cost function, so and all the details needed for the optimization. And the last parameter is the device. So now, because we are running it on our computers, we set it to -1, which means we run it on CPU. If you have a GPU, you can set it to 0, or the GPU, if you have more GPUs, you can specify which GPU you want to run on, and then the computation will be much faster. It will be automatically done on the GPUs. So this is kind of transparent. You don't really, if you have more computational power, you just change one number, and all optimization will be done much more efficiently running on the available hardware. So in this case, it's kind of designed to run in parallel, and the code is parallelizable in an easy way. This is how the chainer, TensorFlow, all these frameworks are designed, so that you can use these features of your hardware to run the optimization. But for now, we have -1 because, of course, we run it on the CPU.
So -1 the CPU, and 0 would be
your first GPU, 1 would be like your second GPU, if you have 2 or more, so yeah, so you can specify. Usually if you have a GPU, it's 0.
Okay.
So this is updater, and then we have the final step, if you remember this figure. So you are done with green box. Now we will define the trainer. We basically give the updater to the trainer. That's not much we need to do. So we just say use our updater, and then how long should we run? We say, okay, we'll run this for 100 epochs. Epochs means number of times you go through the whole data set. So these batches, let's say, are size 40, and there are 351 rows. So roughly we need to run it, the number of batches is basically the size of the data set, number of rows, so the number of samples divided by the batch size. So this is the number of iterations you do in one epoch, and then you say, okay, let's run for 100 epochs.
There's no repetition when you
There will be no, so I think this is because now we do the shuffling, we do the repetition, like resampling, So it simply probably will calculate it as, because this is the definition of an epoch. Epoch is like the number of iterations you use to complete your whole data set. So the complete data set is, let's say, 1,000 rows, samples, and your batch size is 10, so you need 100 iterations to, in principle, to go through the whole data set. But of course, you do this shuffling, sampling, so it's not that you exactly will go through all of them, but this expected value of iterations you will need. So we will set 100. But again, this is a hyperparameter. You have to set it yourself. And by observing the result of the training, and I will show you as the last thing today, how can you monitor the progress of your training. And actually, this will be put in the result folder. So when we run the code, we will have the output of the statistics in the result folder. So this is the name of the folder where we want to have all the information about training. So this is also very easy to specify. And finally, extensions. So what kind of reports we want to have during the training and when. And the first thing, so we want to evaluate our model, and this is where this test iterator comes in. So once the training is performing, we say again, this will be done on the CPU, so please take the data from the test iterator and run it on the model and evaluate how the model behaves on data that was not used, or the portion of the data that was not used for the training. This is a dump graph. This will be just somehow show you, I mean, it's maybe not the best way, but I just put it in case you would like to see this. This dumps a computational graph. So all these frameworks that we see here, like TensorFlow, Chainer, these are kind of it's a programming paradigm. So you kind of you build a computational graph, and this is for the purpose of running this code in parallel on GPUs. So in order to have this, there is a way how actually under the hood these algorithms or all this code is implemented, and we can show this. We can actually visualize this graph. This will be output in this dot format. One way to visualize this is to use this GraphVis software. It's online. You can also just paste the dot file into this website, and it will show you the graph. But also the chainer will also produce a PNG file, so I can show you.
We get an attribute error that the module has no attribute on graph.
I also had this problem. I don't think, it seems to me that this has to do with the version of the Python, because I run it on another computer when I have a different Python version, and it seems that this is causing the problem. So I don't have a current solution. I don't know exactly what is the command for the other Python version. Here I think I have 3.0. So for me, now it worked. But yesterday I tried on a different computer and I had the same problem. So basically you will not see the graph, but you have to maybe check the documentation of what, for your version of Python, what would be the proper command. But you can just ignore it. It will work without it. I had the same problem yesterday.
Is it normal that I get epochs labeled with the same number more times in a row?
The same number.
Like it has epoch 18, 18, 19, 19. Yeah, the values are the same actually, so.
Value can be the same.
But I just found
this one, you mean?
Well, I think all of them, except the first one. Yeah, all of them. They're all double. I guess it's more of the aesthetics issues. They're all the same values, so.
Or maybe if you have maybe more, I don't know.
Also, how?
So these I don't even know why. Like you have the multiple times the output. So this is strange.
They're the same
Maybe you
values.
can check this. I check. And I will just explain that a little more. So
exactly the same number.
this is maybe not that important, but for us at the moment, but in general you can take also a snapshot of your model. So when you do the training, so that you don't restart every time from the beginning, you can ask that every 20 epochs there will be like a image of your model, what is current parameter to be written in a file. And if you need, you can restart from that. You can load this snapshot and restart your training from that point so that you don't need to start from scratch from the beginning. So you can ask that the progress is kind of flashed to the files, and you have the versions of your, during the training, you keep track of your.
So how would we call that snapshot back? How would we get back to this?
There is a, I don't show it here, but there is a function to load. So you basically, when you have the model, you can load the file to, like, I think if you take this trainer extend snapshot, they should also provide a link to the function which allows you to load the file. So this is in the case you would like to restart your training from a given model. Okay, so this is it. So I just kind of provide you different what can be these extensions as a skeleton, so that you can see what. Of course, there is more that you can do, but just to keep it kind of generic. Then we can keep a log report. So basically, what also will be output to the screen, it will be also saved in a file, so that we have the log. And finally, we can have two plots, which shows us this accuracy and loss function value for the during the training. And these graphs we can look at. So basically, this is the extension. The extension is defined once everything, the updater is given to the trainer, and then we can extend the trainer with this additional reporting elements. So this is just the output, what happens when you actually run the training. Okay. And here is the main loop. So this is the main part. So once now everything is defined, everything is ready, and now we can actually. So I should remove. Clear this. So this is how it looks now. Basically, trainer run, and this does the training for us. So I will just check that I don't have the result file. Yeah, okay, so there's no directory here. So I just run this file, and this is the training. So this is the output. What we are interested in is this loss. So this we see that it decreases, hopefully. So it means that we have some progress in our training. And then we have the validation loss. So this is on the not seen data. So it's the validation at each epoch. We can perform the validation on the test iterator. And then we have the accuracy for the training, for the validation, and the time it took to train. Okay. So basically that's
like I understand that we have the data, so how do I get it from the test data? Because I'm not even using that data, right? And 30% of it I'm not even using it.
Test data is
not the test data, the validation data.
Yeah. So this is the same. So because you have train and test. So test data is given to the it's like kept separate.
Yes.
It's given to the test iterator. So after each epoch, once the network is trained, it will be presented with the test data, but now you don't do the training anymore. You just evaluate. So you just run your network to get these values, and you compare with the actual values that you have in the test, and this is the accuracy. So you check. So you don't do any update, you don't do any training. It's just to compute the difference between the test data and what the network at the current state gives you. So usually this will be worse than the training. Training will be better because it's trained for a particular data set, and this will usually be slightly less accurate. So we can see this here. Well, maybe one more thing. So let's test how after the training, how our model behaves. Actually, this is exactly what test iterator does, but now we will do our manually. From the test data, we randomly select one line. we compute the prediction with our model. So model predictor, we run it on the X, and then we have our prediction. And then understanding is if the value is greater than 0, that this I checked, I hopefully I did it correctly. So if it's greater than 0, it should encode good. If it's less than 0, it should be bad. So we report predicted. So if it's greater than 0, predicted is good. Actual, we see what is the actual in the data set. If this is the negative, then we say bad. This is the predicted value. Let's see what is in the test data set. So you can, once the network is trained, you can see that the answer K predicted good, actual good. Okay? But this is just basically a toy, just to see how prediction can be run, whether it compares or not. But actually, this on a more representative way is done in these columns where you have the validation, which is run on the batches. So it does exactly this, but for the whole batches at each epoch.
Is it normal that the loss graph or the accuracy graph are inverse of each other?
Yes.
Is
So
it
if we go to the results, now here is the output. If you go to this result folder, you can look at the loss. So what is the loss?
Not exactly.
We have two things here. So you can check. This is the loss for the training. So this is the blue line. So we see that the loss is decreasing. Okay.
So the number of epochs is equal to the generations actually, or is that a different thing?
So number of epochs is the number of times in principle the network has seen this whole data set. But the individual optimization is done at each iteration. So each epoch has some number of iterations, which is the size of the data set divided by the batch size in principle. And this is the number of steps you have updated your parameters. So the number of iterations is the number of steps that were taken to update the parameters. A number of epochs is the number of times the network has seen all the data sets. So usually you do the reporting on epochs because individual updates are maybe not that relevant because they, for example, as I said, stochastic gradient descent has a high variance. So it means that this gradient will change many times and maybe the direction, so it is like you could take, because this is all about efficiency, so, and there is a trade-off. So you could think of, okay, I go from this point directly to this point, and this is, let's say, my minimum, or I can take fast but inaccurate steps that in general lead me to the same point. But then it doesn't make sense to look at these individuals, which would be the corresponding to iterations. I want to get to the point where, okay, all the data we're seeing, this is maybe the point where I should be in a good, at least, in the good direction. Because this direction is not good at all. But it's a single step. And if I add all the steps, the general trend is good. So that's how this is the intuition. So that's why I report every, let's say, epoch, not every iteration.
And what will change between epoch 1 and epoch 2? Will it be a different set of weights, or?
Yes.
Okay.
But weights will also be different at each iteration. Because this is the gradient descent. So if you remember, when you had the gradient, you were going with the steps down. So at each step, you change the parameter values. It's just that these changes might not necessarily be the, like I showed here. If you want to do the change in one step, when you see all the data, you would go directly here. But with stochastic gradient descent, you can have a high variance, so it will take you a lot of iterations to reach there. And mini batches is better because it's like an in-between, so this is a trade-off. But when you do reporting, you kind of trust more these parameter values in the epochs, let's say, than at individual steps, because they are more representative of the right direction. This is a little bit of a trade-off, so it's not, you don't take the, like with gradient descent, you always take down. The step is like improving. Here it is not necessarily improving at each, it is improving for individual batch, But with respect to the full data set, maybe this direction is not the right one. And this is from here. So this is like with respect to the full data set, you will go this direction. But on the mini batch, you take it here. But the thing is that since you do it many times, in general, the trend of your movement will be along this line. So this is how you could explain why you look at the epochs. Because individuals are maybe not very good, but the general trend is the proper one.
So if I have like optimizer which like not stochastic gradient, but it finds like optimally, that's like consider the ideal case.
Yeah.
So I have an optimizer which finds optimal solution using all the data set. Okay.
Yes.
You don't have any mini batch.
You take
Use
all
the data set and use this optimizer.
Yes.
So we will see like in every epoch the same loss. I think we will see the same loss in every epoch.
No, because so you will see this. You will see, because this is not the end. The next epoch will take you somewhere here, because you are in a different point of your function.
But I repeat the same operation in every epoch. So I have the whole data and my optimizer finds.
But you have new parameter values. So your values will be different and your function will be, because with different, so this will be the same, because this is the data. But what will differ is because you have new parameters, these values will differ, so your cost function will differ. So you're in a different point in your graph, let's say. And this will go down to the minimum. So if we try to draw it, you have your cost function, and here are your parameters. So, okay, one parameter to keep it simple. So in one epoch you are, let's say, U. So this is your current parameter value. You present the full data set, so you compute the value, and then you compute the gradient, and the gradient says, okay, go this direction. So what I'm going to do, I update my parameters. So now I move from here to here. Here. And now my cost function has a new value. So the loss will be different. It will be not here, but it will be here. And then the next epoch, it will move along, and I am here. So I am going towards the minimum. The problem with mini batches is that I don't do it in this way, but rather I have small steps in between which take me in here. So I want to do the epochs because these should be the good points on the actual line. Okay? And this is a little bit explained in this mathematical explanation of the stochastic, but this is, if you don't understand it, don't worry. This is more like, this requires a higher level, this is like statistics. You look at the data as the data is drawn from some distribution, and you want to approximate this distribution. So I gave it there, but if you don't understand it, don't worry. This is maybe more to understand that these iterations are in the direction of, because we do mini batches, you are kind of, the trend is good, but individual updates are maybe not the best ones. So, and actually you can see it here. Because when you do the validation, you see that some points are, this is like a little bit jumping, maybe not very clear here, but here you could see, and I think in one of the iterations, even in the epochs, you can get actually worse values. But the general trend is improving. So finally you get, the general trend is improving. And let's see how much, we have still 10 minutes, so I can explain a little bit here. What would you see from this graph? So this is what, loss. So one thing you can read from here is that the main loss is higher for the training, okay, so it's going down. And then you see, okay, the validation is pretty good, it goes always down, so the network is learning. But what would you read from this? What would be your conclusion here? Like if you look at this graph, what would you like to see more? Maybe I can ask this way.
Or to flatten out?
Yeah, the flatten of the line.
Asymptotic?
So this would we like to see, right?
Yeah.
Exactly. We don't see it. Seems that there is a trend that it goes down. So this is an indication, let's train more.
Yeah.
So 100 epochs is not good enough. You could try
more.
200. and see whether you flatten. If it flattens,
Yeah.
it means, okay, you are kind of reaching, it doesn't say that this is the end, because it could flatten and then go down again, as you could see in this playground.
Yeah.
But in general, you could say that from this graph, I didn't train long enough. And this is one indication where you see, okay, I started with some parameter, I should change it. I should prolong it and run longer. And of course, here I could use the snapshot, because I hopefully you can set it up that, okay, I take last snapshot, so that I don't need to do all the training again. I load my snapshot and I continue from there.
So this graph is representing the evaluation of the training.
Yes,
Yes.
exactly.
And
And
the,
this is
the training is computational intensive.
very.
And if you just run your output, is that still intensive or not?
No. So if you once the network is trained, usually the computation is very quick. Because you have all the parameters, you don't do the update, you don't have it, you just give one single row for your data, and it just propagates and gives you the output. So it's just a matter of computing this for all neurons, this WX plus B, so it's summation. And if you have GPU, all this is done in parallel. Because you have the nodes, so everything is parallelized. So this is very. This is also the idea. The training is intensive, but once you have the model, it's very fast. And where you can see it, you for sure you use Siri, you use Google Translate, you use all this is quick because the model is trained. It takes ages and huge amount of computational power to train the models. Or you can use your iPhone for recognition. The models are trained. They have pre-trained for you. Of course, there is additional training going when you use it. But in general, when you want to use it, it's very quick. Because the complex model is already there. If you would look at it, you probably don't understand why does it work with all these parameters. But it was trained somewhere on some supercomputer, and then just the parameter values are, even a million parameters in your mobile phone is not a problem, but the exact values, this is the value where it is, and then it is very quick to run. So just to conclude,
A quick question. For the first 5 epochs, it looks more accurate than in the middle. I would expect to start completely wrong and then converge more and more, but in this case, it starts accurately, diverges, and then converges again. That's like the first 5 epochs.
you mean here?
Yeah.
Yeah, but this is because we have the, of course, remember that these epochs we use the shuffling and sampling. So this is more like a stochastic behavior now. So and of course, this is also evaluated on the, so it doesn't have to be exactly down. That's the problem. So this is a little bit what I said here, that you go in the direction. Even these are epochs. Epochs are also not exactly on the line. This is also, there is some deviation. But it's smaller than individual steps. So there is some kind of stochasticity in this, okay? So because you have this shuffling, random selection with repeating, so you're kind of resampling the initial data, but in general, this kind of procedure gives you better results than not doing it. So although you have these fluctuations, you kind of pay this price that sometimes were maybe not exactly accurate, but in general, in the long run, this will give you better results than if you would use it in a straightforward way. Okay? But this is all the kind of research and knowledge about machine learning that is I can present here. So all these techniques are standard, and you will see it. That's what I wanted to concentrate on. That we concentrate on the machine learning elements, which are always there, and not actually maybe very particular implementational details. But understanding this is kind of important. And maybe I make a comment here, because for this course, you do these 2 weeks where we are presenting different like gradient descent, computational things. I know that you might in the beginning not know why we are going there, but the problem is that with this machine learning, there are many concepts which, if you don't really see these basic things, what is a gradient, if I would start to talk about this, you would be lost completely. So we wanted to have you, maybe we pay this price that you have these some additional exercises which in the beginning didn't make sense, but I hope that now you see that if you understand at least the gradient descent, you have some intuition what is going on when you go to these kind of examples, because this is involved. I mean, it's not very simple, and this will be even more complicated next week, because we are going to see a network which we cannot even analyze. It will be consisting of 18 layers, and these layers of millions of parameters, and then you just apply these techniques, you don't really understand the details. So it's also a matter of knowing how to read this code. You don't really focus on every single detail because you will not get the bigger picture. So you have to somehow, this is the tricky part. So that's 5 more minutes. I just quickly go through these. So we had loss. Accuracy, there was a question. Accuracy is different from loss, yes, because we want to have good accuracy. So loss we want to have low, accuracy we want to have high. So when the network is accurate, it's good, right? So we have like 90% of accuracy, which is good. Maybe I will. So you see that the accuracy kind of can stabilize, and then it has these jumps up. So you better look at the loss than accuracy, but the accuracy gives you what is like. Actually, the loss is loss is better for training. Accuracy is better for your feeling how good your model is. And also remember that maybe, this is a side thing. This accuracy you can have a very good model, which is actually a very bad model. Although you look at it well. And one example is when you have rare events. Let's say, and this is a side, last thing. Imagine you have 10 rows, and you have 10 years. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 1. If my model always gives 0, accuracy is 90%. I am missing this one, but this one is crucial. So there is one thing I didn't say because it's too complicated, but I didn't want to blur you and get lost here. Always look that your data set is balanced. In this example, we don't get that good results also because the data set is not completely balanced. Actually, there are more bad or goods, I don't remember, but there is not 50-50 or close to 50-50. But just this extreme example. You always return 0, and you think, wow, my model is 90% accuracy. And this is a nonsense model. I mean, it always gives you 0. So you never capture this, okay? So with this, we have to be careful. But this is just a side remark. And last thing, what we could see here. Okay, so snapshot, these are the same models. And this is just this computational graph, which you normally don't want to see and you don't look at because it's not much. But you can see how the computation is done. So you can see that you have this 40, so this is the batch size, 34 is the input, and you have the B, which is 68. These are the parameters in your first layer, and then you have 68 times 34 matrix for the first layer. So this is the representation of the first layer. So in this graph, you can see how many parameters you have. So 68 plus 68 times 34. So one layer is encoded in a matrix. So all the parameters are in a matrix form. So you have this much. And then a linear function is applied. So with this, you get an output, which is 40 times 68. This is the output from the first layer. Then you apply the VLOO function. This is what we specified. And this is an input from the next layer, which is 40 times 68. And now we have the 68 plus 68 times 68 parameters. So this is the second layer. This is the linear function applied. This is the output ReLOO once again. And finally, the last layer, which is 1 neuron, which accumulates everything. We apply the linear function, which gives us the one output. 40 is the batch size. So usually you have this, it's in vector, so it takes the whole batch and outputs the whole vector because it's faster, more efficient in this way. So this 40 is the batch size. And then it has only one parameter, which is used for basically for the classification. So, and for the loss function, so it outputs this, applies this sigmoid cross entropy, which is the which is the loss function, and this is the output. Okay. So this is how the computation is done, and this is like an implementational detail which is done with the GPU. This is useful for GPUs because then it sees what can be run in parallel. So the flow is everything which is on that one layer here can be run in parallel and can speed up the computation. Okay, so thanks for today. This is basically all. We will put a small exercise. This will be basically the same execution, just you play with the different parameters. And you compare kind of the training. Okay, you can use like this. You look at these visualizations and see how, if you play with the parameters, how good the training is and whether you can fit your data. So this is this week, and next week we will go for images. So you should, where you have your notebook, the place where you have your... Yeah, so the imaging is accuracy loss function.
In the morning? I don't see any sense to do that every day. It's a question because you get so tired here that you lose everything across you are doing today, across the lessons. It's nonsense. It's disaster. I know, but for me it's not important. It's just
So
to get.
if you have any questions, I'm still here. You can ask. If not, this is for today.
You should first.
Probably we run the... We start the kernel.
You should start.